Hi, let's convolve two normal random variables, see how that works. Proposition, which we're going to prove. Let x be a normal with mean mu x and variance sigma x square. Y be a normal with mean mu y variance sigma y square, independent. Then x plus y is normal with mean mu x plus mu y and variance sigma x square plus sigma y square for any parameters, any real mu x mu y, any positive sigma x sigma y. Okay, that the expectation of the sum is the sum of the expectations. That's not a big deal. That the variance of the sum is the sum of the variances is not a big deal again, by independence. What is the big deal, what is the interesting content of this statement is that we still get normal. That's the non-trivial part. Okay, let's prove this, and I'm going to do it in two steps. Case 1, I'm going to take for the moment mu's to be 0. I'm going to assume that the mu's are 0. I have 0 means I have some non-trivial variances, but 0 means. And let's do it in this case. Okay, so f of x plus y at a point A is by definition, or not definition, is by the convolution properties we just derived, is going to be the integral from negative infinity to infinity of the density of x at a minus y and the density of y at y dy. Okay, so let's do this. Integrate from negative infinity to infinity. So I'm going to have a 1 over root 2 pi in front of fx, a 1 over root pi in front of fy, so I factor those out. And I have an exponential of minus a minus y square over 2 sigma y square, and an exponential of minus y square. This is actually sigma x, sorry. This is sigma x, and exponential minus y square over 2 sigma x, sigma y square here for fy dy. Okay, this is the integral I need to calculate. Notice that the means are 0, so I don't have to subtract anything further here. That's all I have. And for a while I'm going to concentrate on the exponent. So when I multiply together the two exponential functions, the exponents add up. So I'm going to factor out a minus 1/2 from these exponents. So I'm going to say that this is 1 over 2 pi integrate from negative infinity to infinity e to the minus half times something, and that something I'm just going to denote by this blue bracket here. So I'm going to concentrate on the blue bracket. The blue bracket is everything I have in the exponentials after factoring out a minus 1/2. So the blue bracket is going to be an a minus y square over sigma x square and a y square over sigma y square. That's what I have in the blue bracket. Okay, and I want to find out what this thing is. So I want to simplify this thing. Now, if you look at carefully this formula, this is a quadratic polynomial in y, and I have the integral of a quadratic polynomial up in the exponent with respect to y. The trick is always make it a full square. We have to make this into a full square. Something of the form of a constant times y minus some stuff square and possibly some other stuff, but all of the y dependence should be as y minus some non-y terms squared. Okay, that's the aim, and once we do then you see that it's quite easy to integrate out to evaluate this integral. Okay, so in order to do that, I'm going to break this up a little bit, and I'm going to find out about the factors in front of y squared first. So if I break up this square, then there is a y square coming from here. So there is going to be a 1 over sigma x square and the 1 over sigma y square in front of a y square. That's the first term which I know. So this comes from the square of y here and the other term square of y there. Then there is going to be a minus 2a over sigma x square times y. That's coming from the cross product between a and y when I do the square with a factor of 2, and there is a minus sign there. And then there is going to be a constant term, a square over sigma x square. So this was my first step. I can also rewrite this common factor here as sigma x square sigma y square times sigma x square plus sigma y square. The first term is giving me 1 over sigma y square. The second term is giving me 1 over sigma x square. So I can make this a bit nicer this way. And that's actually a term I want to factor out. So I want to write here sigma x square plus sigma y square over sigma x square sigma y square times, and I want to factor this term out from the first two. So that is going to give me a y square and then minus. So I have a 2a and I have a 1 over sigma x squared, but the sigma x squared is actually factored out. However, I have some more factors here which I didn't have before, so I have to cancel those by adding in this factor of sigma y square over sigma x square plus sigma y square times y, and then I have the a square over sigma x square. So I just did some algebra here. If I redistribute this term over to that one, then the sum of the sigma squares cancel, the sigma y squares cancel, and I'll get back the other term here. Now I'm ready to make my my full square. So now that I have all these preparations, now I'm ready to do my full square. Okay, so I have this factor in front, sigma x square plus sigma y square. I have the sigma x square plus sigma y square, oops, that's a product, downstairs. And now I can say that this is the square of y minus something. What should I write here to make this a full square? When I do some term here and do the square of this difference, then I have the y square, which is fine. And then from the cross product, I need to arrive to exactly this linear term in y. And in order to do that, if I write a sigma y square over sigma x square plus sigma y square, if I do this, then the cross product between y and that term twice will exactly give me minus 2a sigma y square over sigma square sigma y square times y. Okay, so this way all my y dependence is now put into a full square. However, I have an extra term when I square this constant here, which extra term I didn't have there. So I have to get rid of that by subtracting sigma x square plus sigma y square over sigma x square sigma y square times the square of all of that, which is a square sigma y to the 4 over the square of sigma x square plus sigma y square. And then finally I still have this constant from the previous line, a square over sigma x square. Okay, so this way I still just rewrote the previous line. If I cancel out, oops, I forgot to add this square there. If I just put this thing together with the square there, then those cancel, the cross product will give me this term, the square of y gives me that term, so it's still equal. And now there is a lot of cancellations which I can make. I can cancel out one of these sums here, and I can cancel out 2 of the sigma y squared there, and then I can actually factor out some things. I can factor out an a square, and I can factor out a sigma x square, and that will give me this term here in front, sigma x square plus sigma y square over sigma x square sigma y square, y minus this stuff a sigma y square over sigma x square plus sigma y square to the full square, and then I have a minus a square over sigma x square as a common factor, a square over sigma x square in both. Then I have a sigma y square over sigma x square plus sigma y square, and then I have a minus minus, these two minuses together will give me the plus, minus minus of, well, I factored out everything, so this is just a 1, okay, which further equals to, so now let's simplify this a little bit further, which further equals to, okay, which further equals to this first term, I just keep it as it was, sigma x squared, sigma y square over sigma x square, sigma y square, then y minus a sigma y square over sigma x square plus sigma y square, all things squared, okay, minus a square sigma x square, and let's make a common denominator here, sigma x square plus sigma y square in the common denominator, and I have a sigma y square from here minus a sigma x square and a sigma y square. And now again some terms will cancel. I can cancel out the sigma y square here first. So then I have minus sigma x square left, which cancels out with that minus sigma x square. So I can cancel the minus signs and I can cancel the sigma x squares. And in fact the constant term is quite nice. It just gives me together a plus a square over sigma x square plus sigma y square. So next I'm going to plug everything back to my integration. So we figured that so we started with an integral, the convolution integral, and we said it's 1 over 2 pi exponential minus 1/2 square bracket integrated out. The square bracket ended up being this thing here, so I'm going to write all of that back into the original convolution integral. So the density of x plus y at a is going to be the integral 1 over 2 pi, and then the integral from minus infinity to infinity of e to the minus 1/2 of all of that big bracket, of all of the previous line, dy, okay? So all of, well, this is gonna be a bit funny space-wise, but we're just gonna curve the line a little bit. So I have the full square, a sigma y square over sigma x square plus sigma y square, that's the full square. And then I have a plus, a square over sigma x square plus sigma y square, all of that inside the square bracket, and then dy. Okay, now why is that a nice thing to do? Why is that any nicer than the thing we started with? Well, it's nicer because now I'm going to introduce this term here as a new variable. I'm going to call this x. I'm going to introduce that as a new variable x, so y minus a sigma y square over sigma x square plus sigma y square. Okay? And I'm also noticing that e to the minus 1/2 times this constant has no y dependence in it, is just a constant, so I can pull this out of the integral. And then I have 1 over 2 pi. Let's pull the integral out, so, sorry, the constant term out, e to the minus 1/2 of a square over sigma x square plus sigma y square. So I have that term. And then, well, I actually notice, I notice that I also want to include the square root of all this in my x. Let's do it that way. So I also want to include the square root of sigma x square plus sigma y square over sigma x square, sigma y square. Square root of all of that into my x. Let's do it. It's gonna be nicer that way. Which means that if I take a square of this, of all this x, that's exactly what I see here. So all of this together will give me an x square. All of these two terms together give me an x square. So when I do my integration from minus infinity to infinity, the integral itself is becoming very simple, integral of minus 1/2 of x square with this substitution here. It's just an affine transform of y, some constant times y minus some other constant. If y went from minus infinity to infinity, x will still go from minus infinity to infinity. And because of that, dy is just going to be a factor of dx. So dy is going to be the same as dx times a factor. So that factor is just the reciprocal of that root. So the reciprocal of this, which is going to be sigma x, sigma y over the square root of sigma x square plus sigma y square. This is going to be my dy. Okay, so from here. So dy is just dx times reciprocal of all that. I realized that there is an error. Sorry for that. From the beginning, I was missing a sigma x and a sigma y. And that's because of the densities have a sigma x and a sigma y. So there's going to be a sigma x and a sigma y here, downstairs. Just coming from these two densities with some variances, I was missing that. And that will come multiplying the whole integration. Sorry for that. And now that I have those, then I can cancel those out, and I arrive to what I want to arrive to. So I could redistribute the 1 over 2 pi into a 1 over square root of 2 pi. So I could add here a square root and write another square root of 2 pi there, so that I'm distributing the 2 pi into the square of its square root. And then this integral here is just the integral of the standard normal density, which we proved before is 1. E to the minus x squared over 2, 1 over root 2 pi, that is 1. And so that's just disappearing from the whole picture. The sigma x, sigma y, now that I corrected it, will cancel out, and I arrive to a normal density 1 over root 2 pi root of sigma x squared plus sigma y squared times the integral is 1, e to the minus a square over twice sigma x square plus sigma y square. And that's all I have left, which is a normal density. You can read off that this is in the form of 1 over root 2 pi, some constant, e to the minus a square over twice the square of that constant. This is a normal density. It's the density of a normal random variable with mean 0 because I'm not subtracting anything from a underneath the square, and variance sigma x square plus sigma y square because that's what I'm dividing by underneath the a square. Okay, taken at a, from which I conclude that x plus y has this distribution, normal of 0 sigma x square plus sigma y square. Okay? All right. That was case 1. That was case 1 done when the means are 0. So the means are 0, x plus y is then normal with mean 0, variance sigma s square plus sigma y square. Let's now do the general case. How does one do the general case? And obviously one could redo the whole calculation with generic sigmas, but that's of course not what I'm going to do because that would be even messier than this calculation. So general case, I have the general means and variances. Okay? Right. And they are independent, of course. Instead of redoing the whole calculation, I'm going to recall that an affine transform of a normal is going to be a normal again, and you just need to change the means and the variances. In fact, I only need to subtract means. So let's start looking at the sum of these two, which I want to have the distribution for. And let's write x minus mu x and y minus mu y, which is of course not equal, but it is going to be equal if I add back the means. And now I can say the following. X minus mu x is still normal, but its mean is now 0. So it's normal with mean 0, variance sigma x square. Y minus mu y is still normal, but its mean is now 0. And the variance is sigma y square. And of course, if x and y were independent, then these guys are still independent. So now I have two normal random variables independent with mean 0, and case 1 was exactly for this scenario. Mean 0 generic variance. So when I add them up, if I add these two up, if I convolve the distributions, if you want, or add up independent copies, then according to case 1, it is giving me a normal with mean 0 and variance sigma x square plus sigma y square. Okay? And now if I add a constant, namely mu x plus mu y, to my normal, this whole thing together will now have the distribution of a normal increased from 0 to mu x plus mu y, and the variance kept at sigma x square plus sigma y square. And that's the end of the proof, because that's exactly what I claimed here. If we add up two independent normals, then the means and the variances add up, and more importantly, it stays normal. That's what we arrived to. You might wonder if it's so easy to transform out the expectations from normals. So we have normals with general means, but we can easily transform this out to get mean 0 normals. Why did we carry on with the sigma squares in case 1? Why did we do this proof in such a complicated way with all the sigmas there? Why can't we just factor out the sigmas and scale that out too? And the answer is, if you think about it a little bit, is that you can actually square out one of them. You can make one of the sigmas to be 1 by factoring out something, but you can't do it both at the same time. So you need to carry at least one of the sigmas. And that's all the simplification you can do in case 1, which probably doesn't worth it, but anyway, I didn't do it.